Good morning, everybody. Happy Monday. Geez, it's been a while since I've seen you guys. You guys, of course, had a short week last week, and then we didn't have class. So we can start with some green check marks and let me know how you are doing. That'd be great. I also wanted to maybe discuss the learning guide, and I know Mrs. Ward gave you guys some practice provincial exams at the last field trip, so just wanted to speak to that as well. But yeah, just check in for now. Yeah, we're still on Unit 8. We have one section left. We'll do it this morning, probably take maybe like about an hour or so to get through it all. Hopefully. It always takes longer than I think, but it's graphing, and you guys have practiced your graphing skills in math already, so you guys would be experts already on this stuff. And then we get into Unit 9, which is on acceleration, which is just more of the same stuff. It all looks the same, and on the provincial exam or on a test, everything looks the same. So there you go. All right, so everyone's good. Perfect, clear those out. What I want to do is maybe just look at the course and just point out a few things, and we basically only have about... Okay, perfect, Taylor. We'll get to those. We only have, about 3 classes worth of material left, or 3 lessons left, and then we just have some review, and then the provincial exam. So everything kind of just happens really quickly now through the end of the course. So if you're in the course, we're on Unit 8 right now. We're going to cover graphing motion here today. And then once graphing motion's done, then we're going to jump into Unit 9, which only has 2 sections. So it's super, super quick, and that'll be Unit 9. So we'll definitely finish the course. I hope to finish the course this week. We'll finish Unit 8 and 9 this week. So there you go. And then Unit 10 we've done already. This was Earth Science, continental drift, and all that stuff. So really just Unit 9 left. The very bottom, you'll see this provincial exam section, and there's some different things here for you guys to go through if you want. I'm not going to make any of them mandatory yet. So final review vocab. This is just a PDF of all the vocabulary terms that we've covered so far this year. So I'm not a huge fan of just memorizing definitions and words, but if you go through that and it's I forget if it's I might as well open it up. If it's alphabetical or if it's broken down by unit. I think it's broken down by unit. No. Oh, yep. Biology, chemistry, physics, earth science. Perfect. So broken down by unit. So if you go through that and you see a word, you're in chemistry here, and you see something like, indicator. I don't remember what an indicator is. So maybe that's worth going back and looking at that and trying to figure it out. All that stuff's there. So those are all the important vocab words that you'll need to know. Like I said, not worth memorizing them all, but I mean, if you see something you've never seen before, then it'd be worth looking it up. The other thing we have here is a topic checklist, which is exactly what it sounds like. It just goes through each of the kind of learning outcomes from the course, and you should be able to do all of these things, such as use standard atomic notation to identify the atomic number and mass of various isotopes. So do you know what an isotope is? Atomic mass number. So you can go through that, and again, if you see something that maybe you haven't seen before, then you could go back and look it up. So the provincial I gave to Mrs. Ward to give to you guys was an old provincial I had, and that's this guy right here. It's called Practice Provincial. Now, I'm not going to insist you do it right now, but what I want to do is I want you guys to have it. If you didn't go to the field trip on Wednesday or Thursday last week, you didn't grab one, that's fine. You can just download it, but it's kind of long. Obviously, like 80 questions, multiple choice. Some pages only have 1 question on them just because of diagrams and whatnot. So it was just there for you guys to not have to print off as much. And I mean, you don't even really need to print it off if you have a digital copy, but it's nice to work off paper. So if you open that up and start going through those questions, then it's good to kind of, look at the questions, how they're asked, get used to the format of the exam. They're always the same. Yep, Taylor, it's 80 questions. The questions from each kind of section don't really change. So the number of questions from chemistry and biology, it's always the same. They just kind of change the questions a little bit. So it's worth just flipping through for now. The one that I gave you guys, and this one here, Practice Provincial, this is the one I'll go through with you in class. We'll go through it question by question. I'll give you some hints on how to get rid of, a few answers usually and things like that. And then if you click on this other one, Practice Provincials, this is just links to the 4 sample exams that are online on the BC Ministry website. So you can go to the BC Ministry of Education website. If you just Google BC Provincial Exams, it'll come up, and then you will be able to access all 4 of these exams and answers to those as well. I have an answer key for the exam I gave you, but I want you guys to go through it first without looking at the answers and then come back after and check the answers. So I'll put up a key to the exam I gave you maybe at the end of this week or beginning of next week. And there you go. Kind of a weird time, right? We're trying to review for the provincial and then finish up our course material at the same time. And it can be a lot all at once. But we're just going to zip through the end of the physics unit, and then we'll have time to just focus on reviewing. But there's not really a lot of classes left. We do like 2 or 3 classes a week. There's only 3 weeks left before your exam. So kind of crazy how fast the year goes. So that's that. I'm going to spend more time talking about the exam and the types of questions and things like that once we get through the course material, but I just wanted you guys to have that exam and access to it, and we'll start talking about it maybe at the end of the week, depending on how far we make it. So the practice exams and the exam that I've given you are always the same 80 questions and multiple choice, no written or anything like that. No short answer, no long answer, 80 multiple choice, that's it. So there you go. Taylor had some questions from Unit 8. Maybe we can get to those now. And I would be happy to go through them. Or if anybody else has any questions. So we've basically finished up to page 5 in the data or the learning guide. And we're going to talk about graphing motion today, which is page 6, 7, and then that's it. So there's only kind of 2 pages left, and we haven't talked about them yet. So anybody else have anything? Page 5, 13, and 15. What's the average velocity of a car that moves 60 kilometers in 3 hours? Okay, look at number 12 on page 4. Yes. All right, 13, 15. How far can 25 minutes at 12 meters per second? I'll just give you the formula for 13, and then I'll do number 15 for you. So the average velocity formula is on the back of your data booklet. So VAV, the average velocity, is your change in position over your change in time. And you have your change in position is 60 kilometers. So that goes on the top here. And then 3 hours goes on the bottom. So 60 divided by 3 is going to end up with 20 kilometers per hour for that guy. Number 15 is a little trickier because we have some units to watch for here. We have 25 minutes and then 12 meters per second. We need to be careful that we're using the correct units and that they match up. So I have the data book here. Maybe I'll just jump back. We're asked to find how far, and that is a distance. So we need to know what the distance is. So if we go to our data booklet, you can see I've even highlighted it because the last question we looked at was the same thing. So the distance equals the velocity times the time. So we're going to use that. D is VT. Now, we're either going to have to convert minutes to seconds or 12 meters per second to meters per minute. Now, we never really talk about meters per minute. That doesn't really make sense. We're meters per second or kilometers per hour. So I'm thinking the easiest bet here is to convert 25 minutes into seconds. And then once we've done that, we can plug the information into the formula. So if we have 25 minutes, we want to get rid of minutes, and we want to end up with units of seconds. So if I have minutes on the top, I want to get rid of it. I'm going to put it on the bottom, and I want to end up with seconds. So I'll put it on the top. Now, what is the relationship between minutes and seconds? Well, hopefully we remember 1 minute is 60 seconds. We're going to use this unit cancellation type thing to figure out how many seconds are in 25 minutes. So we're going to go 25 times 60. We're going to end up with 1,500 seconds. And we have minutes canceling minutes, and we're left with seconds. All right, from there we can say, okay, we have our units matching up. I have seconds here, I have seconds here. That's a good thing. So I will take my velocity, which is 12 meters per second, and I'm going to multiply by my time. Now my time was in minutes, but now I've converted it to seconds. My S's are looking like 5s this morning, and I'm confusing myself. 1,500 seconds. And I'm going to end up with 1,500 times 12, which is 18,000 meters. Now we can say 18,000 meters, there's nothing wrong with that. It doesn't give us a direction to deal with. We're just assuming everything is kind of positive, and we don't know what positive means in the particular question. So 18,000 meters is fine. We could write 18 kilometers as well. That would be an acceptable answer. When we get really big numbers in meters, sometimes it makes more sense to convert it into kilometers, just divide it by 1,000. And sometimes that happens on exams and quizzes. You'll get an answer in meters like we've just done, but all the multiple choice answers will be in kilometers. So you'll get 18,000, but there'll only be an option of like 18 there. So just watch your units, it's really important. Hopefully that helped. Number 12, page 4. Displacement is change in position between 2 seconds and 5 seconds. So here we are at 2 seconds, and here we are at 5 seconds. So this guy went from here, moving across to there. So at 2 seconds, he was at 2 meters, and at 5 seconds, he was at 7 meters. So usually when we write down displacement, the actual definition for displacement, it's a vector, so sometimes you'll see a little arrow over top of it like that. It's a change in position. So it's your final position minus your initial position. And we haven't written anything like that before. And if you don't want to think of it in terms of that, that's fine. You can just think about where did he end and where did he start? And what was the change? How far did he go? So if I started here, I've gone 1 meter, 2 meters, 3 meters, 4 meters, 5 meters. And what direction? That was 5 meters to the east. That's all you really need. Or you could talk about something like this. You had 7 meters minus 2 meters is 5 meters, and then you look at the direction east. It doesn't really matter how you get there, as long as you are coming up with something like that. That's good. Now I'm just reading this last question asked here. For some questions that we don't talk about directions, such as 18 page 5, they still put a positive sign in the answer. With questions like this one, number 18 here, there's no real mention of direction and everything's just positive, so that's fine. If the question doesn't give you any direction, you can't give a direction. If all of the numbers you're given are positive, then your answer's positive, then that means that your answer is in the same direction as the initial sort of parts of the question. If your answer is giving you a negative, then that means you're going the opposite direction that was originally happening, but you don't know what that direction is. You don't know if you're going now south and everything in the question was going north. So given a question like this, you can't be really specific with your answer just because you don't know. You don't have to make up a direction. You can only use the information you're given in the question. So you don't have to get too carried away with direction. If no direction's given, then you can't just make it up. So there you go. It's just kind of one of these things that we can only work with the information you're given. Hopefully that's okay for that. I'm going to go through the graphing stuff, and then we'll come back to the learning guide and we'll just take a quick peek. And if you have any other questions, we can go through them. So we're going to jump to 8.3. My laser pointer here. All right. This is graphing motion, and I've said this before, but you guys are really good at graphing, so you guys should have no issues with this stuff at all. At least I hope. And yeah, it's pretty straightforward. So time interval and position, we're going to talk about these things together. So initial time is when an event begins, and then final time is when an event ends. Now we use these little i's and these little f's, they're subscripts. Ti is the initial time and tf is the final time. One thing that I will mention that if you continue on and take physics with me next year, assuming I'm teaching physics next year, sometimes textbooks and teachers won't use I for the initial. Sometimes we'll use a little zero, and it's called T naught or T initial. So they mean the same thing, it just depends on who your teacher is and the notation they're going to use. Sometimes it'll be Ti, and sometimes it'll be T with a little zero next to it, but they both mean the same thing. So just a kind of a notation type thing. The time interval is the difference between the initial and final time. So you always go final minus the initial. Wherever you ended minus where you began in terms of time tells you how long the event took. So we've looked at this little skateboarder already, just in the last question. And it's the question I'm asking you guys is, what is the time interval to move from the hydrant to the sign? What's the time interval? Almost the exact same question we just looked at. So how long did that take? Any ideas? Now with questions like this, the numbers are really small. You can just work it out in your head. Perfect, Haley, thank you. 5's right. But what you're actually doing is you're taking the final time. 5 minus 2. Sorry, Taylor. You're taking the final time, which is 5, minus the initial time, which was 2. So 5 minus 2 gives you 3. So the event took 3 seconds. Even though at the sign, you're 5 seconds, the event, which is from the hydrant here to the sign, only took 3 seconds because you're at 2 seconds, 3, 4, 5. And you're here. So 5 minus 2 gives you 3 seconds. So that's what you're doing in your head. 5 minus 2 gives you 3. So that event took 3 seconds. If we wanted to know from the tree to the sign, that would be 5 minus 0, which is 5, and that event would have taken 5 seconds. And what we don't want to do is, I think what you're doing here right now, Taylor, is you're kind of confusing your position and your time. And the question is just asking about time. So it doesn't even matter where this person is, how fast they're going, anything like that. So don't confuse yourself by mixing up the distance, position, anything like that with the time. It's just asking about time. So you could just go, okay, at the hydrant, that was 2 seconds. At the sign, that was 5 seconds. 5 minus 2 is 3. It took 3 seconds. It doesn't matter where he was. 2 meters here, 7 meters here. Has nothing to do with the time it took. So try not to confuse the values. Moving on. We're going to talk a little bit about uniform motion, more so after the break, but for now, it's the definition. So uniform motion is an object that's not speeding up or not slowing down. It's traveling at a constant rate. And a lot of times in physics textbooks, you'll see pictures like this, where what they basically do is they turn a camera on in a dark room, and then there's a strobe light, and the strobe light flashes at a constant rate. So the ball's moving across the table, and every time the strobe light flashes, light hits the ball, and then gets developed on the camera. So it's a really, really good way of being able to figure out how far an object's moving in a given amount of time, because a strobe light will flash whenever. If you want it to flash 5 times per second, you can set it to flash that many times. But it's not speeding up, it's not slowing down, and it's not changing direction. This is the important part of uniform motion. So uniform, whatever that means to you, uniform motion is just an object that's moving the same amount of distance in the same amount of time. So how can we tell from the picture here if the object's moving in uniform motion, or if an object weren't moving in uniform motion, what would that look like? So how could we tell the difference between uniform and non-uniform motion given an image like this? Any ideas? How can we identify uniform motion in this picture? Or if uniform motion were not happening, what would that look like in a picture? So it wouldn't have equal distance. That makes sense to me. So each flash, the ball is about the same distance apart for each flash. So this distance is the same for each one. So if it were traveling, if it were speeding up, then the flashes happened at the same time, but the balls would actually be a little bit further apart. So this ball would maybe be over here a little bit. And same if it was slowing down, the balls would be a lot closer together. They wouldn't be as far apart. So yeah, perfect. We'll actually look at an example of that here in a second. So there you go. That's uniform motion. We're going to talk a little bit about graphing. And one kind of tricky thing that happens is we're going to spend some time talking about position time graphs. So plotting an object's position as a function of time. So at any given time, where is the object away from some point? Now, we're going to spend a bunch of time talking about position time graphs, and then all of a sudden we're going to talk about velocity time graphs. Now, in class, it makes sense. Everything we talk about now is position time. Everything we talk about later is velocity time. But on a test or a quiz, it gets really tricky because sometimes you'll be given a position time graph, and then the next question will have a velocity time graph. And you need to be able to think, what is this graph showing me? So make sure, please make sure when you look at a graph, you always check the units on the axes. So is it a position graph versus time, or is it a velocity versus time? Most graphs will have a nice title, like this one does, position versus time. If they don't, you'll be able to identify a position on this side and then time down on the bottom here. So it's really important that you're able to identify the difference between the two, and all that means is just reading what it says. And it seems really obvious, Mr. Borden, why would I make a mistake and confuse these graphs? When you're kind of, head down, flying through a test, you see a question, position time, velocity time, you're not reading your units very carefully. It happens a lot. So the position time graphs always look the same. They have position on the vertical or y-axis, and they always have time on the horizontal or x-axis. This best fit line is really important. Jumping all over the place here. Best fit line is really important, and it's not actually shown here. And I'm going to have to show you what I mean by best fit line. So remind me to do that when we jump to the learning guide later. I'll draw some diagrams for you and show you what a best fit line is. Uniform motion is represented by a straight line on a position time graph. So if we have a straight line, that means we have uniform motion. And we can get lots of information from this graph, and you guys are well aware how to do that, so I'm not going to spend a ton of time talking about it, but we'll maybe just look at some examples. So we can end up with kind of 3 different scenarios, and this is just the exact same as the last stuff we did in math class. The position side, what does the right brackets mean? The right brackets. I think it has, the word right, that's just telling you the object's moving to the right. So it could say left in there, it could say up, it could say down. It could also have like a north, south, east, west in there. It's just indicating direction, which is, I could see why that would be a little bit confusing. So yeah, just the object's moving to the right. So 3 scenarios. You could have positive slope, which goes up to the right. Up to the right, it's backwards for me. You could have zero slope, which is a horizontal line. And then you can have a negative slope, which goes down to the right. So what do we think a positive slope means? Looking at the first graph up at the top here, you see that it has a positive slope, it's going up to the right. If we were to describe this motion, what would we describe as happening here? How would we tell somebody what was going on in this graph? It's one thing to look at a graph, but it's another thing to understand what's going on there. So if you had to explain this to your little brother or sister, what would you say was going on there, the first graph? In a couple words, doesn't have to be super elaborate. It's going up. So if those brackets said centimeters left, then the negative slope would actually be to the right. Ooh, that's going to be the 3rd example, so we'll definitely get to that, Abby. It's going up. That's a common thing that students will see happening on the graph here. What does it really mean, though? We have position in centimeters to the right. So at 0 seconds, I'm at 0 centimeters to the right. After 1 second, I'm at 20 centimeters to the right. And then 2 seconds, I go up and across, I'm at 40 centimeters to the right. 3 seconds, I'm at 60. 4 seconds, I'm at 80. 5 seconds, I'm at 100. So is the object moving up, or is it moving in some other direction? It is, in fact, a positive slope, and it is increasing its position, but is it going up? Is it moving off the ground? Is it going in the direction up, or is it going in a different direction? A little bit tricky, I guess. So the graph here is telling us that this object's moving to the right. So when we see that the line is increasing in terms of slope, or going up and to the right, the actual object isn't moving to the right. The object is starting at 0, then it's moving to 20, 40, 60, 80, and 100. So the object's basically, you could think of it as kind of like a ball, or my little laser dot here, and it starts right here, and it's just moving to the right with uniform motion. So the object isn't going up, it's just moving to the right. How about the horizontal line, or 0 slope? Again, if you were to describe what was going on here, how would you describe what was happening to somebody. The second graph, horizontal line, what does that mean? What is the object actually doing? And think about it in the same way I just looked at the other one. If you're at 0 seconds, where's the object? If you're at 1 second, where's the object? If you're at 2 seconds, where's the object? This one's maybe a little bit confusing. Nobody wants to take a stab at this one. It's actually quite straightforward once you really think about it. Of course, this is the first time you've seen it. All right, so at 0 seconds, the object's at 2 meters to the right. At 1 second, the object's at 2 meters to the right. At 2 seconds, the object's at 2 meters to the right. At 3 seconds, the object's at 2 meters to the right. 4 seconds, 5 seconds. You get the idea. The object's not moving. It's completely stationary. Perfect, Ava. So it doesn't matter what the time is, the object's still at the same spot. 2 meters, 2 meters, 2 meters, 2 meters, 2 meters, 2 meters. So the object's always 2 meters to the right. So if you see a horizontal line on a position time graph, that means your object's not moving, which is different than a velocity time graph, which we'll get to here in a second. The negative slope, the last picture here, and Abby kind of alluded to this before, we've done positive slope up and to the right, we've done horizontal line, now negative slope. What's going on? If you had to describe this to somebody, what would you say the object was doing? So think about it like we've done the last two. At 0 seconds, you're 1.5 meters to the right. At 0.2 seconds, you're 1 meter to the right. At 0.4 seconds, you're half a meter to the right. And then at 0.6 seconds, what does it mean when it crosses the x-axis here? What does that mean? And then at 0.8 seconds, you're negative half a meter. And now anything above the axis here is to the right. Anything below the axis is going to be to the left. So you're half a meter to the left. At 1 second, you are 1 meter to the left. So what was going on? And Abby, you mentioned something before. Negative slope would actually be to the right. Is that what's happening here? Is this object moving to the right? Or something else going on here? I mean, you can always draw a picture to try to figure out what's going on with this stuff. Like maybe a little stick figure or even just a ball. And just trying to figure out what's going on. So a negative slope is representing negative movement. Then would a negative slope represent a positive movement? Oh boy, we're getting deep now. All right, let's look at what you're saying here. So would a positive slope represent a negative movement? Then would a negative slope represent a positive movement? Yeah, I guess it's kind of confusing stuff. A negative slope just means the object's moving opposite to the direction indicated on the graph. So on this graph, it says going to the right. So if we see a negative slope, that means the object's moving to the left. Let's maybe draw a picture of this. I think I have this loaded in. Yes, I do. All right. Let's just maybe look at the last one here. Just supersize this a little bit. But it says to the right. All right. Let's start with some object. I'm going to start with a tree. There's my tree. And I'm going to say, I think you are, but you guys have never seen this before, so that's why we're talking about it. Your tree is at 0 meters. Are we happy with that? Does that make sense? So I'm going to have a kind of like a ruler along the bottom here. And my tree is my origin, or 0 meters. I guess I can just do this. Should be fine. All right, so there we go. So I have 0 meters. This is 0.5 meters. This is 1 meter. This is negative 0.5 meters and negative 1 meter. And I have some object. I don't know. Let's make it just a red ball. Now, I guess I need 1.5 out here. Okay, so I have this red ball. At 0 seconds, my red ball is 1.5 meters to the right of something. Okay, we all happy with that? That's this point right here. 0 seconds on my x-axis. The object's 1.5 meters to the right. Okay, now 0.2 seconds passes. This is where I'm looking now. And my object is 1 meter to the right. So now my red ball's here. This is 0.2 seconds. What happened to the ball? Well, the ball is just kind of cruising along, going that way. It moved from there to there. All right, let's look at the next one. The next point says at 0.4 seconds, my object is 0.5 meters to the right. So here's my red ball. This is at 0.4 seconds. So again, the ball just is kind of rolling to the right. This point right in the middle where I have my objects crossing this axis, the x-axis, what does that mean? Well, at 0.6 seconds, my object is 0 meters to the right. So this is 0.6 seconds. And you can kind of imagine at 0.8 seconds, my object is 0.5. And then at 1 second, my object is at negative 1 meter. Does that make a little bit more sense to just describe the object moving like that? If we draw it out on a nice little diagram. So the object's just a ball rolling along. Remember, the negative sign is just indicating direction. Just means it's moving towards that tree, and then it moves past the tree. It doesn't stop at the tree. Nothing fancy happens at this middle point at this 0.6 seconds. It's just an object. It's kind of rolling along, and then it passes the object, the reference point. In this case, I drew a tree. It could have really been anything. I kind of get it, but you still put the ball in the left direction. I didn't choose that. That was indicated by the graph. Maybe I'll just scroll up here and we'll look at the one at the top. So this is a position time graph. This is the one that was at the top. There's the 3. So this is a positive slope. I'll just quickly draw what this one looks like. Let's have another object. Let's start with a tree again because my trees are pretty good. All right, so that's 0 meters. And then I have 1 meter, 2 meters, 3 meters, 4 meters, 5 meters. I could do the same thing going to the left. Could have negative 1 meters, negative 2 meters. Get the idea. All right, let's draw our red ball here. At 0 seconds, the ball is at 0 position. All right, so this is at 0 seconds. Then I look to my next point here. At 1 second, my ball is, I did 2, but I should have done 20. Let's change the scale of my line here. 20, so this is 10, 20, 30, 40. This is negative 10, negative 20. Hopefully that's all right. So at 1 second, the object is 20 meters, and in this case, it tells us to the right. So my red ball is here, and again, that's at 1 second. It's 20 meters to the right. And then the next one, so my ball rolled to the right a little bit. The next one's here. At 2 seconds, my object is 40 meters to the right. So this is 2 seconds. And that's just going to continue. The ball is just going to keep going. At 3 seconds, it's going to be 60 meters. So if I had another point out here, there's 50, there's 60. Draw the red ball over here. And that would be at 3 seconds. So the ball is just moving to the right. That's what the positive slope is indicating. Now I don't want to confuse you, but it can get confusing. Now, our graphs in the first example here said centimeters to the right. And I could just as easily have a graph that said centimeters to the left. There's no reason the graph couldn't be plotting an object moving to the left. Now, normally in physics, we think of things that are going to the left as being negative. But there's no reason it has to be that way. That's a completely arbitrary decision on our behalf. If you think about it, in North America, we read from left to right. That's just how we do things. But if you're in Japan, they read from the back of a book and they read from top to bottom. So it's just kind of like, well, they read from essentially right to left. They read backwards through a book. So maybe if I was teaching physics in Japan right now, I would have everything to the left was positive and everything to the right was negative. It's a completely arbitrary decision. We've just made this decision. It's not right, it's not wrong. We've just decided it's just going to be that way. So it's kind of where it gets a little bit confusing in terms of this stuff. So just be careful. Watch your signs and watch what you're graphing, your units, things like that. So we've done positive slope. In this case, it was an object moving to the right. Negative slope, it was an object moving to the left. And then horizontal line, zero slope, just an object wasn't moving. It was just completely stationary. So those are the scenarios you're going to encounter. You probably knew it was coming. And when I was in grade 11, I took physics. And my physics teacher said, if you see a graph and you don't know what to do, find the slope of the graph. Just always. Every question you don't know what to do, you come to a graph, find the slope. That's going to get you almost guaranteed a mark in any physics question. The slope of a graph is always really important. And you guys spend a lot of time finding slope. Now, in math, we talked about slope being rise over run. And the rise was the change in x, the change in y over the change in x. Now, we're in physics, and we're not talking about x's and y's anymore. Now we're talking about position time graphs. So if you look at the slope formula here, this thing's so sensitive. The slope formula is change in position over a change in time, which is just the exact same thing as what you guys did in math, except it wasn't change in d over change in t, it was change in y over change in x. You've already done this. I've just changed the letters from x's and y's to d's and t's. Now, you guys are really good at finding the slope. The only thing that's kind of getting in your way is students tend to get confused. As soon as you see d's and t's instead of x's and y's, you're like, it's so confusing. Abby, the arrows above the letters indicate that these things are vectors. So D is going to be position, arrow over top because the direction's important with that. Something like time, we don't have any way to indicate a direction for time. It's not a vector. So we don't have a little arrow over the top of it, which is a good question. It's just a notation thing. Some teachers will use it, some won't. I think it just confuses students, especially at the grade 10 level. It's just an extra thing in there that you don't really need to know for the questions you're doing. Even when I was in university, my professors didn't really insist on the arrows. It's just kind of assumed if you've made it that far. So I'm not going to, spend a ton of time describing this formula, but we're just going to, maybe do a couple examples. I will for sure, Taylor. We'll look at them. let's, instead of doing like a calculation, let's just talk about in terms of like an idea. So we have two joggers here. We have a position time graph. We make sure always check our units. So we have position, meters forward. We don't know what direction it is, just forward. And then time. So we definitely have a position time graph, and you can see the title even says position time graph, which is really important. We have jogger A and we have jogger B. And we can look at the relative slopes of these two lines. So jogger A, jogger B. They're both starting at 0 seconds and 0 meters, which is kind of seems strange, or doesn't seem strange, I should say, but we'll look at it, some examples of when that doesn't happen. What is the difference between these two joggers? Who is faster? Who's slower? What other information can we get from the slopes of these lines? Maybe instead of thinking about calculating the slope in terms of numbers, we'll just look at the slopes compared to one another. Which one's steeper line? Which one has a steeper slope? Jogger A or jogger B? And then we'll kind of figure out what that means, maybe. So no numbers yet. Steeper slope belongs to jogger A, jogger B. Jogger A, jogger B, jogger A, jogger B. Jogger A is going faster because the slope is steeper, question mark. I think you should have just lost the question mark there, Ava. But let's look at it. Okay, so jogger A here. Jogger A was running 20 meters in 5 seconds. So I go across 20 meters, 5 seconds. Jogger B ran 16 meters in 8 seconds. Let's maybe pick a point that crosses both these. At 5 seconds, where was jogger A and where was jogger B? So we know they both started at the same spot at 0 seconds. At 5 seconds, jogger B was at 10 meters. And at 5 seconds, jogger A was at 20 meters. So jogger A has a steeper slope. That means jogger A ran 20 meters in the same amount of time that jogger B took 10 meters. So 5 seconds, jogger B is at 10 meters. 5 seconds, jogger A is at 20 meters. So clearly jogger A is faster because jogger A is moving a greater position or greater distance in the same amount of time. Hopefully that makes a little bit of sense. All right. I'll talk about velocity. Yeah, let's do this. We'll talk about velocity, and then we'll maybe take a break after this. There's about 3 or 4 more slides left. So average velocity. The slope of a position time graph is the object's average velocity. So slope is velocity on a position time graph. Like I said, if you don't know what to do, you're given a graph, you find the slope, that's going to mean something to somebody, probably going to give you a mark. Again, I'm going to look at the graph. I'm going to make sure I know what type of graph it is. So I can see that it's a position time graph. I have position on the y-axis and time on the x. It even says position time. You'll see a lot of graphs like this. They don't actually have numbers. This is T1, T2, T3. I got to quit doing that. You can make these times whatever you want. You can make this 5 seconds, this 10 seconds, this 15 seconds. It's not important to the question. The graph is just saying, at this time interval, the object's here. At this time interval, the object's here. And at this time interval, the object's here. We don't always have to put numbers on these things. Sometimes numbers just confuse us. So what's going on? Could we describe what was happening to this object without numbers? I don't know how far it's going, but could I describe kind of general or relative motion here? At 0 seconds, it started at the beginning, which is 0 position. I have a positive slope. I have a horizontal line or 0 slope, and then I have a negative slope. What is going on with this object? We know what a positive slope means. In the example we looked at before, that remember the ball was moving to the right. And then a horizontal line or 0 slope, the object was stationary, not moving. And then a negative slope, the object was moving back from where it came. So if I were to describe the object here, I'd say the object was moving away from where it started. Maybe then the object took a little break, and then the object moved back to where it started. At 0